Today we're going to work backwards with composite functions. We're going to start with the composite and we're going to pull them apart. F of g of x, a composite function, contains an inside and an outside part of this function. So if I start with f of g of x, remember f of g of x is evaluating f of x at g of x. So if you look at this visually, you can see that g of x has to be the inside function and f of x is the outside. So g of x is the inside and f of x is the outside. So what we need to do is pull them apart. And there are some tips to do that. We're going to look at 4 basic cases to give you a model to go by. So if you want to pull a composite apart, the first thing you need to do is to look for the inside function and label that. We want to make sure we can identify it. So these inside functions are usually located in a denominator. So if it were a function that looks like y is equal to 1 over x plus 3, you could say the inside function was the x plus 3. An inside function can also be found inside what's called a transcendental function. Well, what the heck is a transcendental function? It's one that is not an algebraic function. So examples of transcendentals are y is equal to the sine of x, the cosine of x. Those are transcendentals. Y is equal to e to the x, or log functions. All of those are transcendental functions. So the inside function would be whatever is representing the x in this case. They would all be inside the transcendental. An inside function could also be the base of an exponent. An example would be y is equal to, let's say we have some polynomial base 2x plus 3, and that is raised to the 4th power. Okay, so the inside function there would be the 2x plus 3. So once you have your inside function identified, what you're going to do is you're going to label that. You're going to label the inside function as g of x because, again, we are evaluating f of g of x. So g of x is the inside function. And then, once you have g of x, whatever that expression is, you go to your original problem and you're going to replace that expression that represents g of x with just the variable x. And what that does, again, we're working backwards, that gives you your outside function. So you identify the inside function, you label that as g of x, and then you go back and you replace whatever that inside function is with just x, and that gives you f of x. So that's how you separate your inside function and your outside function. So we're going to work through some examples, and in these examples all we are doing is pulling our composite function apart. So we want to identify an inside and an outside function. Our first example is f of g of x is equal to the cosine of 2x. So this is a transcendental function. I want to find my inside function, which is going to be g of x. So g of x is going to be whatever is inside the transcendental. And here we have the expression 2x. So my inside function is the expression 2x. Then what I do, I'm going to replace whatever this is with just the variable x. And that's how I get my outside function. So f of x is the cosine of x. So it's really not that bad. Here's my inside function and here's my outside function. It's important to do this. I know it seems simple now. It's important to do this because when we get to the end of the year, we're going to be doing some calculus where we have to identify the inside and the outside function when we get to something called the chain rule. So here's my next example. F of g of x is 3x squared plus 5x plus 2, all raised to the 5th power. So now we have a base, that's an expression. This is going to be my inside function. And whatever that is, raised to the 5th power, that's going to be my outside function. So g of x is 3x squared plus 5x plus 2. That's my inside function. F of x will be the expression I get when I replace all of this with just x. So f of x is x to the fifth. And to check it, you can work backwards again. If you were to process f of g of x, then you would be processing f of x evaluated at 3x squared plus 5x plus 2. And that would lead right back to our original expression. So we use composites to define inverse functions. Now we won't be doing this particular process much, but we do use them to define inverse functions, which is what I'm going to talk about next. So if I'm given two functions, f of x and g of x, then those two functions, f and g, they're going to be inverses of each other if this happens. When I process f of g, I get x. Or when I process g of x, I get x. Because if you think about it, if two functions are inverses of each other, then one is undoing the other. It's like taking x, adding 3, and then subtracting 3. You're back at x again. Or taking x, multiplying by 2, and dividing by 2. And when you perform inverse operations, you're left with the original. So that's the definition of inverse functions. And what we're going to do is just practice finding inverses algebraically. This is review from last year. There's just one particular case that I want to focus on. So if we're going to find the algebraic inverse of a function, we have to first think of the notation. And if I'm given a function f of x, the notation for the inverse is f negative 1 of x. Now that does not mean you take the reciprocal of it. I know if we use negative 1 as an exponent, that tells you to take the reciprocal of the base. That's not what we do here. That just represents finding the inverse of f of x. So to do that, it's relatively simple. Basically, we're going to switch x and y, and then solve for y. So you switch x and y. If you start with f of x, you replace f of x with y, and then you solve for y. So basically by doing that, you're undoing all the operations. You have to perform all the inverse operations to get back to y again. There's some relatively simple examples. The one I want to focus on is when you have an even root, because this is the one that everyone forgets. If you are undoing a square or something raised to the fourth power, you have to remember the original could have been positive or negative. So that's the example I want to show you next. Okay, so here's an example. Given f of x is x squared minus 1, find f negative 1 of x, which means find the inverse algebraically. So we're going to start off. F of x is the same as y, so if I rewrite it, that's really y is equal to x squared minus 1. I'm now going to switch x and y and solve for y again. So x is equal to y squared minus 1. You switch x and y because that forces you to do all the inverse operations to get back to y. So the first thing we do is add 1 to both sides. I have x plus 1, and that's equal to y squared. And then we take the square root to get back to y again. Now, if you are taking an even root, you have to add the positive or negative. Okay, any even root needs the positive or negative in front of it. It's not true with odd roots. Odd roots only have a single beginning. They can start off, and when you take the cube root, you can take the cube root of a negative number and you'll get a negative answer. So it's not the same with odd roots. Only even roots. So f negative 1 of x here is positive or negative, plus or minus the square root of x plus 1. And we're going to practice more of these examples in class. We'll practice pulling apart the composites and then finding the inverse algebraically.